My name is Diego Serrano, and I'm a MEMS development engineer at Qualtrics. I'm also a member of the integrated MEMS group at Georgia Tech. And today I'm going to be discussing some of the details on the design and analysis of MEMS gyroscopes. So probably the best place to start our discussion on MEMS gyros is by defining what a gyroscope is. So a gyroscope, or a gyrometer, or a gyro for short, is an inertial sensor that measures the angle of rotation or the rate of rotation of a particular object. And there are many different ways in which you can do this. Probably one of the most conventional ways of doing it is by using this spinning type gyros, in which what you do is you take a spinning wheel and you rotate it really fast, and that creates a very strong angular momentum which resists any force that tries to change its orientation. So that basically serves as a very stable reference in space, and then you can use, for example, a gimbal structure around it to measure the relative angle of that axis of orientation with respect to the gimbal around it. Another way in which you can detect rate of rotation is by using this so-called Sagnac effect, in which optical gyroscopes are generally based on. So the way that it works is you have a laser source in which you have two laser beams that are going in different directions. And when you rotate your structure, basically the time that it's going to take for one of these beams to reach the destination is going to be shorter than the time it takes for the other one. And then by measuring this delta of time, you can estimate how fast you're rotating your object. A more recent type of gyroscopes that are under a lot of research currently are this NMR gyros, or nuclear magnetic resonance gyroscopes, in which, very similar to the spinning wheel gyro, what you do is you take a very stable reference and you measure your angle of rotation with respect to that particular reference. But in this case, instead of using the angular momentum, what you use is a very precise precession rate of particles when they're exposed to a nuclear magnetic field. They're exposed to a magnetic field. So probably the gyroscopes that are of most interest for us are these vibratory type gyros. And the reason they're interesting is because they basically don't have any moving parts, unlike the spinning type gyros, in which you probably have a lot of bolts and screws. But these are composed of just a solid type of resonant device. And the reason this is important is because that allows us to scale them down in size. So, and that's what basically today's talk is about. How can we make these micro-machined vibratory structures that can actually be used to sense angle of rotation or the velocity of rotation of an object. So the reason MEMS gyroscopes have received a lot of attention in recent years is because they have enabled a set of applications that were not even possible to implement before the devices were invented. And an example is what we see in the automotive industry. We can place this very small, very low power type of devices and measure, for example, how a vehicle is rotating about a certain axis, and then use different control schemes for anti-skid control or for rollover control. Another example is in the industrial space. Now we can place this very small, very precise type of devices in, for example, unmanned vehicles that can go into harsh environments. And the reason MEMS gyros are attractive is because, as I mentioned before, they don't have any moving parts, so they're usually more reliable and can survive a lot better this vibration and high shock that are experienced in this type of industrial spaces. Probably the application space that has received the most attention in recent years has been consumer. And this is probably because gyroscopes have been a success story in this particular space. Not only because they have been able to measure rotation for gaming applications, but because now we see them in a little bit more advanced type of applications like optical image stabilization, in which you can measure how a person is moving or shaking their hands while taking a picture. And basically you can compensate for that and get much clearer images. Another reason why this space of applications is of great interest is because now that we have these very small sensors that we can actually integrate into handheld devices, this opens the possibility of actually implementing applications in which we can track the motion of a person in an enclosed space. So if we have accelerometers and gyroscopes, then we can know precisely where a person is, for example, in a building where you don't get GPS access. So obviously this is a very good alternative for applications in which you don't want to rely on the signals, like also in the military space where usually GPS can be easily jammed by an enemy. Now, in order to get a better understanding of where gyroscopes are today in terms of performance, it's always good to take a look back at how this type of structures have evolved. And in this particular example, we can see here a gyro from the consumer space for STMicroelectronics reactors gyro. And one thing to note here is that one of the parameters that has evolved over time is size. So in the consumer space, size is obviously critical because real estate in the PCB boards of this consumer electronics is very expensive. So throughout the years, we can see that these companies have pushed to try to reduce the overall die area. In the case of the Steve Gyro, they have been able to reduce the overall volume of their package by a factor of about 4x. And very similarly, if we take a look at Invenson's gyroscopes, which is probably ST's biggest competitor in the consumer space, we see that very similarly from 2006 all the way to 2012, their overall die size has reduced by a factor of 3.5x or so in terms of volume, not only the die area. On top of this, they have been able to go from a biaxial gyroscope to a triaxial gyroscope in the same die volume. So obviously, in consumer electronics, small size and low power are critical. But if we really want to be able to enable this new set of applications like pedestrian navigation, what really matters is performance. And if we see how things have evolved throughout the years, particularly for these two main companies, we can see that they have done a pretty good job in reducing the overall size of their devices. This has been a combination of changes in their mechanical sensor and in the electronics. But one thing to note here is that today we're still at least an order of magnitude off from where we want to be to get to be able to do some navigation at least for a few seconds. And another important thing to note is that the trend of this noise reduction is starting to taper. So obviously that makes us wonder if perhaps this particular type of sensors are reaching their fundamental limit, and it might be time to look into a new kind of technology. And part of today's talk will be around this topic, what other different type of devices are out there that can either perform better than the conventional type of structures, or at least reach. Yeah, so those are all our commercial gyros that this is happening. So the reason I don't make a fair comparison here, I don't talk about it, is because this device is a lot larger in size compared to what Invention we have. I'm not wrong, it might also be a single axis because it's 3 axis. This is ionic, so and It might be EPI. I don't remember what to use, but it's just other competitors that are not strong as ST and Inventions in the consumer space. So now let's take one step back and talk a little bit about the fundamentals of how vibratory gyroscopes work to have a better idea of how to design them to get them to perform better. So probably most of you know that vibratory gyroscopes operate by using this physical phenomenon known as the Coriolis effect. And perhaps the easiest way to understand how this principle works is by looking at the classic example of the Foucault pendulum. So if we have a pendulum that we place exactly at the north pole of the Earth and it's swinging back and forth, if we have an outside observer, so someone, for example, in outer space, what that person is going to see is that the swing of that pendulum is always going to be about the x-axis. So if we assume that there are no other damping forces or there's no interaction between this string and the rod that supports the pendulum, there's no reason for this pendulum to change trajectory in the global coordinate system. So even though we can have rotation in the Earth, for that outside observer, the trajectory is always going to be about the x. Now, if we have a second observer that is actually on the surface of the Earth, and let's say that coincidentally one morning his house is exactly along the x-axis when he wakes up in the morning. So when he comes out of his house and if he takes a look at this pendulum, what he sees is that proof mass moving back and forth towards and away from him, right? It's sitting right here, looking in this direction. You're going to see the proof mass moving back and forth. Now, as the day progresses for this observer, what he starts noticing is that if he keeps looking into the center, towards the center of the Earth, what he sees is that the trajectory of this pendulum is actually changing. So in his own coordinate system, the way this pendulum is moving looks different. And then about 6 hours later, when he's exactly 90 degrees away from where he woke up that morning, what he sees is that the trajectory now is no longer towards and away from him, but that pendulum in his own coordinate system is moving from side to side. So one thing this observer notices is that the acceleration at which this pendulum changes its trajectory is actually proportional to the velocity of that pendulum, and it's also proportional to how fast the day has passed, and basically that's how fast the Earth is rotating. So basically he can, if he's able to measure that acceleration that he's perceiving, and he knows what the velocity of the pendulum is, he can back calculate what the rotation of the Earth is. Now, another important thing this observer notices is that early in the morning when he woke up, all of this oscillation was taking place along the x-axis. But then later in the afternoon, when he was 90 degrees away, all of that energy that was originally stored in that x-axis oscillation, he perceived it as an energy transfer into another mode of oscillation about the y-axis. And then the reason, because the reason why it's important to describe things in terms of two sets of oscillation about the x-axis and the y-axis, and then any motion in between can be described by a linear combination of these two modes, is because that's exactly how we usually design MEMS structures. So what we usually do in order to get this micro machine devices to operate is we design them to have a particular mass, similar to the pendulum. We have that proof mass swinging back and forth. That can be modeled as a lump element parameter of two sets of second-order systems. And these two systems are one about, in this particular case, the x-axis. So this structure we design it to have a particular spring that allow it to move back and forth about the x-axis. And then another system that has compliance about the y-axis. And then if we, for example, excite this into an oscillation in the x direction, when we apply rotation rate to our frame of reference. Well, part of that energy, similar to what happens in the pendulum, transfers to our y-axis. So we can model this by using two separate second-order system equations, one for the x-axis mode, one for the y-axis mode, and both of the systems are coupled by our Coriolis effect. Our Coriolis acceleration times the mass gives us a force that is going to transfer the energy back and forth between these two systems as we rotate the structure. Now, when we first started today's discussion, we said that a gyroscope is an instrument that can measure either the angle of rotation or the velocity of rotation of an object. And one interesting property that vibratory gyroscopes have is that we can actually configure them to operate in a particular way so that our output is either proportional to our rotation rate or proportional to the angle of rotation. And in general, usually rotation rate gyroscopes are of the tuning fork kind, and whole angle mode gyroscopes are either axis symmetric type of structures like shells or rings or discs. But that doesn't mean that we can't use a tuning fork gyroscope in the whole angle mode option, or that we can't operate a shell type gyro, the rotation rate sensor. The reason why I say that this is the typical way or the typical structure that we use in this particular type of operation is because each one of these has certain advantages that will become a little bit more clear as we continue this talk. So in the case of the rotation rate gyroscopes, what really makes them different from a whole angle mode gyro is the way we excite our device and the way we sense its output. So for the case of the rotation rate gyro, very similar to what we have been describing, we excite one mode, in this case about the x-axis, into vibration or oscillation, and if we don't have any rotation, this sends deformation or deflection is equal to 0. And then we apply rotation. Obviously, part of the energy that we inserted into that drive mode transfers into our sense mode, and then the amplitude of that vibration in the sense is proportional to our rotation rate. Now, the difference between this approach to what we described for the Foucault pendulum is that we keep dumping energy into these drive modes. So basically, unlike the Foucault pendulum, where all the energy of the drive was transferred to the sense, in this particular case, we made sure that this energy is always being replenished and that amplitude of the drive is being kept constant. And later on, we'll see why this is important to make sure that rotation rate gyros operate properly. On the other hand, whole angle mode gyros operate slightly different. So what we do here is if we take, for example, this shell-type device and we excite it into its first elliptical mode of vibration, so basically it's just expanding and contracting in this particular shape. And we make sure that we only excite this into vibration once, so unlike here where we keep dumping energy into this mode, we just hit it once and assume that our energy losses are very small, so basically that's going to keep vibrating forever. When we apply rotation to that system, what happens is that the anti-nodes of vibration, so basically where the maximum points of vibration occur, do not rotate at the same rate as the frame of reference that we're rotating. So basically, if we have electrodes placed orthogonal to each other, we can measure the amplitude of the two electrodes and estimate what the angle of rotation was. And later on, we will cover in detail what whole angle mode gyroscopes are, and I'll describe why is it that this standing wave doesn't really rotate at the same rate as the rotation applied. But let's first focus on rotation rate gyroscopes because these are As far as I know, the only commercial gyroscopes available, at least in the MEMS space. I know that there are some whole angle mode commercial gyroscopes, like the HRG from Northrop Grumman, but there are still no, to my knowledge, any microstructures that operate in this type of mode. So going back to the rotation rate gyroscopes, as we have described, there have two modes of vibration. Generally, this mode 1, we call it the drive mode. So, as we mentioned before, we excite this into oscillation by, for example, applying an electrostatic force through an electrode located parallel to the vibrating structure. Now, once we have established this constant vibration, we have a reference velocity that is similar to the velocity that we have in our Foucault pendulum. And then when we applied angular rate, we have the Coriolis effect that is going to generate a Coriolis force, that is basically the Coriolis acceleration times the mass of the system. And if our vibration is, for example, about the x-axis, like in this particular case, and our rotation is about the z-axis, then since this force is the cross product of that rotation rate and that the direction of that velocity, that force has to be along the y direction, and that basically excites our second mode of vibration. And then we can, by knowing the parameters of this second order system or that particular mode, we can measure that deflection and back calculate what the input rotation rate was. Now, in general, this type of gyroscopes are operated by establishing oscillation. Yep. Yep.
When you start under Coriolis force to start oscillating in the y direction, is there a counter effect, a dipole effect?
There is, yes. So, as I mentioned, there's always an energy transfer between the two modes. So, the way you take care of that, and I think that will be covered in more detail during the interface circuit session, but in general terms, the way you take care of that is by guaranteeing through control electronics that the amplitude of vibration of your drive mode is always constant. So you have an amplitude gain control system that compares that to a reference and keeps it stable. Mm-hmm. All right, so going back to the way we operate this gyroscope. So in general terms, what we want to do is establish an oscillation around that x-axis mode, or well, in this particular case, it's about the x-axis or mode 1. And going back to your question, where you would place that amplitude control circuit will be somewhere around this chain. So basically, you monitor either this amplitude or this amplitude, and then you feed it back to this amplifier. So you control the gain of that amplifier to make it constant with respect to our reference. And obviously, where we want to establish this oscillation is at the resonance freak of that mode. The reason we want to do this is because if we take a look at our simplified second order equation from our well-developed model, we see that that location and frequency is where we get the most amount of displacement for the least amount of force. We get this amplification factor. And if we simplify our expressions, replacing our frequency of operation right at the resonance frequency of the device, we notice that that transfer function from force to displacement is actually proportional to the quality factor of that mode. So basically what this is telling us is that if we want to have a system in which we don't have to put a lot of energy into to get a particular amount of displacement, well, we want high Q. And this is why in the case of tuning for gyroscopes, we usually need very low pressure environments. So basically we have to go to pressure levels in the millitore range in order for that Q to be higher and get a larger electromechanical transduction. Now, in order to establish that mechanical oscillation, obviously we need a transducer to convert our electrical signal from our amplifier into that mechanical displacement. And in commercial gyroscopes, probably the most common type of transducers are capacitive or electrostatic transducers. The reason for this is because they're easy to fabricate, unlike, for example, piezoelectric transduction. You don't need any additional layers that might add cost to your process or that might add some additional temperature variations. And in terms of the electrostatic transducers, we can either utilize them as a parallel plate type of device in which the deformation happens perpendicular to that plate, and the advantage of measuring changes in capacitance this way is that this particular change per unit change of gap is inversely proportional to the initial gap you have squared. So what this is telling us is that as we reduce our gap size, we get a much better change in capacitance per unit of deflection. And since it's a square value, that means that we have very good electromechanical coupling. On the other hand, we can also implement column drive actuation or sensing type of structures. Now the difference here is that the motion of the mechanical device is not perpendicular to the faces of our gaps, but actually it's in parallel. And what this enables is to have a much linear transfer function, so we don't see this dependency on X anymore, but that comes at the expense of much lower electromechanical transduction, so you don't get that squared function anymore. So in tuning fork or low frequency type of gyroscopes, these column drive structures have been extensively used because, as we will see later, the overall noise or the Brownian noise of tuning fork or gyroscopes in general is inversely proportional to our drive displacement. So if you want low noise, obviously you want to have a very linear electromechanical transducer to get a much larger deflection. Later on, we will also see that there are ways to get around this by playing with other parameters, and you can actually get very good noise performance even for small deformations or small deflections. So once you have established this oscillation about your drive axis, well, as we have been describing, the velocity of that drive mode multiplied by our input Coriolis rate, which is the Coriolis force, and then that is going to excite the sense mode. And what we actually get at the output of that system is a signal that is proportional to that rotation rate, but it's modulated on top of the frequency of the drive. So in order to be able to extract this rotation information, we will need to use electronics to demodulate that signal. So basically, take it apart from its carrier, and that can be easily done, and we will be explaining in detail in the next session, by taking the drive mode as a reference and using a conventional demodulator or multiplier, and then you can just extract that signal of interest. So now, if we take a look at the ratio of our sense displacement per unit of drive displacement, which is actually a very good metric to see how good of a gyro we have, because this basically tells us how much energy from my drive mode is actually going into my sense mode per unit of rotation rate. When we look at the transfer function, what we notice is that it is a function of both the resonance frequency of the drive and the resonance frequency of the sense. So now the question is, well, where are these frequencies with respect to each other? And that's what actually determines the different types of rotation rate gyroscopes. So if we, for example, have a gyro that has drive resonance frequency that is lower than the sense resonance frequency, we usually say that this device is operating in a mode split condition. The modes are not on top of each other. And when we look at that metric of sense displacement per unit of drive displacement, what we notice is that it's obviously proportional to our Coriolis term, and it's inversely proportional to the resonance frequency of the sense mode squared. So what this basically tells us is that if we want to have more energy transferred from our drive to our sense, we need to make this value of omega sense as small as possible. And we will talk about how can we do this. The next type of operation is mode-matched gyroscopes, in which the two resonance frequencies are equal to each other, and then we get a great advantage from operating a gyroscope in this mode, because all the energy from our drive is going to get amplified by the quality factor of the sense. So, unlike this case, where if you have your drive frequency here, you're only going to get about this amount of displacement. In this particular case, you get this 2 times higher effective transfer of energy. Now, going back to what I was describing, in general, but not necessarily, most split gyroscopes are of the tuning fork kind. Mode-matched gyroscopes are typically axis-symmetric type of devices, but again, this doesn't mean that you can't operate tuning fork gyroscope as a mode-matched gyro, or a mode-matched gyro, an axis-symmetric gyro as a mode-split device. Some of the key features of mode-split gyroscopes are that, as we mentioned before, the resonance frequencies of the drive and the sense are different, and this is mainly because the mechanisms by which the frequencies are defined are different. So, for example, in this particular case, if we trace a line about 45 degrees, we see that the structure is not perfectly symmetric, which means that what defines the mechanisms that define the drive mode displacement and the sense mode displacement are going to be different. Now, that doesn't mean that you can't change the dimensions of certain springs to adjust them to be equal, but in general, it's a lot harder to get a mode-matched gyroscope when you're implementing it with this type of approach. One of the advantages of operating in mode-split conditions is that you get a much larger bandwidth. And this is because you're not operating in this high Q region, where obviously your bandwidth is determined by the resonance frequency divided by that Q. So you get this type of acceleration type response. So if you remember the previous plot, you're in this flat type of region, so you get a lot more bandwidth. As we mentioned, the scale factor is inversely proportional to our resonance frequency. So as we know, in a lump element model, that frequency is equal to the square root of our stiffness over our mass. So if we want lower resonance frequency, we obviously need a lot of mass. And this comes as a compromise of a much bigger area. And obviously if we want lower spring constant, well, that can be bad for reliability, because now you have a more flimsy type of structure, so it might not be as immune to shock as we want it to be. Now, in the case of mode-matched gyroscopes, as I mentioned, if you implement them using this axis-symmetric type of devices, the modes of operation are inherently degenerate, so basically they're identical because the structure is perfectly symmetric. Now, a possible disadvantage is that your bandwidth is now determined by that quality factor. So if you design a device like this ring that has a frequency in the kilohertz range, and then you have a Q in the tens of thousands, then your bandwidth is probably going to be about 1 hertz or so. So that might not be very practical for certain applications. But there are techniques that you can use to increase the bandwidth through electronics, and that will be covered later on. Or you can design structures that operate at much higher frequencies, and then you get a much larger effective bandwidth. And lastly, as we mentioned, the scale factor is proportional to Q. So if you know how to design your MEMS, then you can get very large quality factors, even up to 1 million. So this is a great advantage in terms of the amount of signal you can get out from these devices. Now, in terms of mode split gyros, if we want to design a good device that has a good scale factor and low noise, if we go back to that scale factor transfer function, we said that if our send frequency is much lower than our drive frequency, or rather the drive is much lower than the send, this whole denominator reduces to just omega 10 squared. So as we said, to reduce that, we need larger mass and lower stiffness, and we can see this in this particular example. We see a lot of regions that consume a lot of area, but give us a lot of mass to reduce that frequency. And we see these serpentine type of structures that really give us a very low spring constant, and that way we can reduce our omega naught of the sense to get a much larger scale factor. Another important thing to know here is that since you don't get the Q amplification, you also need to find ways to compensate for this. So a way to do this is by adding a lot more capacitive area, so you have this interdigitated fingers, so that you get a lot more change in capacitance per unit change of displacement. Now, another.
What's the load? What's the motional load of that?
I think it's so basically the mode of operation is. Are you familiar with STMicro device? So it's basically I can't say exactly for thermodynamics, but from the way it looks like, it's very similar to STMicro device. So basically, what we have is they call it a heartbeat motion. So basically, all these proof masses are moving outwards and inwards simultaneously. And then when you apply rotation, for example, about the x-axis, part of that energy couples into an out-of-plane mode, and then you can measure the relative change in lateral change in capacitance. And then for the in-place rotation, well, the mode shape of this one just becomes a rotational motion, and you get a change in capacitance. I don't know if that answers your question. No, not really. Okay, we can talk a little bit more about it after the presentation. So as I was saying, when you have this low frequency type of structures, you obviously still need high Q, not to get that advantage from your sensitivity, but still you need to reduce the mechanical motional impedance of your device in order to have to put a lot less energy in your drive mode. And to do this, you need very high vacuum environment. And obviously, in order to achieve this, you need to probably use getter type structures in your package to make sure that the vacuum environment doesn't change over time, and this can add some cost to the processing. So now let's move into mode match gyroscopes, and in order to describe the benefits or the way this type of devices operate, I'm going to use a particular example, which is the Bulk-Acoustic wave gyro, which is, in general terms, an active symmetric structure, as we described before, but it's not a shell or a ring, but it's a solid disk. And the fact that it's axis symmetric allows us to have inherently mode match modes. So in this particular case, I'm showing the first elliptical mode of this disk, and we have very similar to what we had for the tuning fork, one mode for driving and one mode for sensing that are orthogonal to each other. So as we see here, the nodes of the nodes, which are the locations where you get zero deformation, coincide with the antinodes of the other modes, which are the points in space that have the maximum deformation. So you can say that these two modes are orthogonal in space. So one of the advantages of operating at high frequency using bulk-acoustic devices is that you get this high Qs even in moderate pressure levels. So unlike the tuning for structures where you need to go through this millisecond range of pressure, here, since you're at much higher frequency, you don't get as much viscous damping on the device. And then again, since you're operating a much higher frequency, well, your device is a lot more robust, and then it's more immune to shock and to vibration. Now, one of the complications is that, again, you have a much stiffer device, so obviously it's going to be harder to drive it into oscillation, but you can get around this problem by implementing very narrow parallel plate capacitive gaps by the use of sacrificial layers. And in the particular case of this gyros, these gaps are in the order of 100 to 200 nanometers, unlike what you see in conventional tuning fork devices where your gaps are usually in the order of 2 to 5 micrometers or so, or even bigger devices can be up to 10 micrometers. So the way these gyros operate is very similar to the tuning fork. In this example, I'm actually showing the second elliptical mode of this device instead of the first elliptical mode. But the operation principles are basically the same. So what you do is you close a loop around your structure by exciting it at the electrodes that are aligned with the antinodes of one of the modes, and as we described before, they coincide with the nodes of the other mode, so there's no cross-actuation. And then in the presence of rotation rate, part of that energy couples into that orthogonal mode, and then the formation of that second mode is going to be proportional to a rotation rate. And you can use electronics connected to the electrodes that align with that second mode, and basically demodulate your signal, as we mentioned before, by using as a reference your drive oscillation. So here's an SEM view of this type of structure. So as we see, we have our disk surrounded by electrodes. This is implemented in a 40 micron device layer SOI wafer, and as you can see from the scale right here, they're very small in size. They're only about 600 microns in diameter. Here's a cross-section view of this type of sensors, and as I mentioned before, since they're so stiff, you need very high electromechanical coupling, so you need to go and implement these very narrow capacitive gaps in order to drive and sense the deformations of these devices. But this can be done with different processing techniques like the HARPS process, which is the use of sacrificial layers to define the gaps instead of just etching through the silicon layer. And those gaps, you can actually control them very well because they're defined by the growth of, for example, oxide. And once you have your structure, then you can wafer level package it. And as I've been mentioning before, you don't need very high vacuum because you're a much higher frequency, and you can get very high Qs, even at 1 to 10 torque pressure level. So in this particular case, I have an example of 77,000, but you can tailor that Q to go up to even 200, 250,000, as Mustafa showed in the previous presentation.
What's the purpose of the whole? Is it for fabrication?
Yeah, fabrication. So it's to release the structure. Yeah. Usually, what you want is the structure to be as solid as possible. So this is just for processing.
What's the cross structure?
So the cross structure is really not a mechanical component. It's only to provide a bias potential to the disk. And the reason it looks like that is for temperature and stress compensation, so it doesn't really affect your performance. It's just you have this flexure type of device. So if you apply stress, it's not going to go all the way down to the center and change the performance of the disc. So now the question is, well, these high-frequency devices, can they really perform at par with tuning for gyroscopes, or can they even deliver better performance? And one way to do this comparison is by looking at every single metric that defines if a gyroscope is high performance or not. And we can start by looking, for example, at the motional impedance or motional resistance. And this is basically a metric of how much energy you need to put into the drive mode to keep that oscillation. So basically, if we look at this function, we see that obviously if we go to higher frequencies, this value is going to increase. So that's actually not good in terms of performance. So if we go, for example, from 10 kilohertz to 10 megahertz, then you're degrading your motional resistance by 3 orders of magnitude. Now, something to note here is that since we've been reducing our gaps to drive this type of devices, because we mentioned that they're a lot stiffer, that is actually compensating for that increasing frequency. And what we see here is that since this is such a strong function of your gap, to compensate for 3 orders of magnitude of loss, you only need to decrease that gap by a factor of 5 or 6. And then on top of that, if you operate in bulk-acoustic modes, you can actually get a much higher effective Q, and that is beneficial for your motional resistance. So actually, this parameter can be optimized to be quite low. Now, if we take a look at the scale factor in terms of the amount of current coming out of a sense electrode per unit of rotation rate applied, what we see is that this transfer function is actually independent of frequency. So you're really not losing anything by going to a domain where you have much stiffer structures. And as a matter of fact, as we said, since we're reducing our gaps, our scale factor is actually improving, and we can get higher Qs with this type of structure, so we can get even better scale factor as compared with tuning fork. Now, if we take a look at the mechanical noise, which basically determines the lowest signal that you can actually measure in your resolution, well, since we said that we need to decrease our gaps to actually get much better electromechanical coupling, well, that really degrades our noise. We said that we need 5 to 6x decreasing in the gap to gain for what we lost in the resonance frequency. So that's a reduction of about 5x in noise, or a degradation of 5x in noise. But again, if we take a look at the complete expression, it is a function of the it's inversely proportional to the frequency, and even though that term is inside that square root function, since we're increasing our frequency by 3 orders of magnitude, you're gaining already 30x improvement in noise performance. And again, you can get much higher Qs, and that can compensate for any losses in mass that you're having from making these devices smaller. So there are ways in which you can actually design this type of structures to be high performance. Now, if we take a look at the bandwidth, we said that for a mode-matched gyroscope, this is proportional to the resonance frequency divided by your Q. So obviously, what we want to have is very high Q values, but if we're in the megahertz range, again, for a Q of 10,000 or 20,000, now your bandwidth is about 100 to 200 hertz. So you get that bandwidth back by just going to higher frequencies. So we just discussed some of the metrics that usually you use to guide yourself to see if you have a good gyro or not. But a good question is, do these high-frequency devices have an additional advantage, or do they have anything else to offer as compared to tuning fork? And obviously, as we've been saying, well, they're a lot stiffer because they're solid state in nature, so they actually have great immunity to shock and vibration. So if we, for example, compare 3 consumer-grade tuning for gyroscopes just from off-the-shelf devices and an automotive gyroscope with a BAW device, we see that in terms of random vibration performance, the BAW device outperforms by orders of magnitude this tuning fork devices, and it's just because it's a lot stiffer. Similarly, if we compare the performance of sinusoidal vibration, so you basically apply an acceleration signal at different frequencies, we see that the BAW device outperforms the industrial and automotive device, and it's almost at par with an industrial grade gyroscope. And again, in terms of shock immunity, outperforms all the consumer grade gyros, and is at par with an automotive part. But something to highlight here is that all these measurements were done without doing any electronic compensation on the mechanical structure. So this metrics can actually be brought down even further if you use, for example, methods of averaging to get rid of these additional sources of error. Now, you may wonder, well, why is this really important? We know that having good shock and vibration immunity is good to have in the industrial space, but in terms of market share, this is really a very small niche. So why do we want to spend time changing our technology to have better performance in shock? Well, something that people in the consumer space are starting to realize is that actually vibration immunity is critical for navigation applications. So if we really want to get this navigation grade performance from gyroscopes that can go in handheld devices, it's good to have vibration immunity. The reason for this is because you can think about vibration as another source of error, and similar to noise, as time passes by in a ray gyroscope, you integrate it out so that leads to drift, so that error starts accumulating with time. So obviously, if you have a gyroscope with good vibration immunity, its CPE is going to be much smaller than the one that you get for a gyro with a poor vibration immunity. So basically, the overall error that you're going to get is much lower. So even in the consumer space, vibration immunity is very important for newer applications. So far we have discussed how to implement this high-frequency gyroscope to measure rotation about the Z-axis. But very similarly, you can do the same to detect X and Y rotation. The way you can implement this type of structures is by, instead of using a disk, you use an annulus, and what you do is you basically excite.
You're talking about the vibration.
Mm-hmm.
That's the axis as a movement that I think typically gyros are axis, so I really will be pulled by the axis in terms of
Yep. Yeah, of course, there is definitely an impact, and that's another advantage you get from using this axis-symmetric sensor-supported type of gyroscopes. In some tuning fork type devices, sometimes you have your anchors on the outside of the sensor, so any stress differences between the corners of the device are going to transfer directly into your sensor. So what people most of the time have to do is come up with this decoupling type of structures to avoid this kind of problem. In the case of this disk resonator, since they're sensor supported, there's a lot less difference between that stress that is going into your device. So that's obviously a good advantage in terms of vibration and stress immunity. All right, so going back to how to implement X and Y high-frequency gyroscopes, we can use an annulus structure, and we can excite an implaned mode of oscillation. And then as we apply rotation about, for example, the x-axis, well, part of that energy is going to couple into an autoplane mode, because as we said, Coriolis acceleration is a cross product of the velocity that you have established, which is in this particular case, let's say the y-axis, and then if you apply rotation about your x-axis, then the deflection is going to happen about z. And then you can basically utilize out-of-plane electrodes to detect that change in displacement that is going to be proportional to your rate. And then if you use a mode that is orthogonal to the one that you're using to detect x-axis rotation, then you can implement a y-axis gyro, actually using the same structure. And then once you have this type of device, you can interface it with electronics, and as we can see here in this plot, you can basically have gyros with very small frequency split, as we've been saying. We want to operate this in mode match condition, and in a few minutes we will talk about how to compensate for errors in gyros that are not perfectly mode matched. And here we can see some of rate response measurements from this type of out-of-plane detection devices.
How do the out-of-plane mode sensitivity compare to different?
Well, it depends on how you design the structure, right? So it depends on several parameters. So it depends on the resonance frequency. As we said, the sensitivity is inversely proportional to the resonance frequency. So if we go to lower frequencies, obviously you're going to get higher sensitivity. But you're going to lower frequencies, so you might not get the same amount of speed. So these two factors might cancel each other. So what we get for our devices is very similar levels of scale factors. And then with the electronics, you can just compensate for any difference to get about the same output range.
You have to switch specific driving out negative, then suddenly it's out of the y-axis sense.
No, actually, you can measure rotation about the two axes just by using the exact same structure. So if you notice here, the antinodes of this mode shape, this particular two antinodes, they coincide with the antinode of this mode, and then these two with these two. So there's always a coupling of energy. Now, the disadvantage of using a single device for two-axis sensing is always cross-axis sensitivity. So if you matched all of your modes exactly at the same frequency, if you have any sort of imperfection, chances are that part of the energy that you're trying to couple from the x-axis into, for example, this out-of-plane mode is going to end up showing up in this one. So that takes me to the next slide, in which. So I don't know if you can see here. So basically, you have a spring-like type of structure, and the only reason to add that is to provide flexibility to let this annulus section, which is what mostly determines your frequency and mode shape, this vibratory spring. So all that the spring structure does is starting to match that vibration to the anchor. So in reality, you cannot see it here. What you have here at the center is just a big anchor. Now, if you design this correctly, you can even place a Z-axis gyroscope right in the middle of that, and then you get a triaxial gyro in a very small area. If you have enough room there for it, we've done it in the past, and the problem is that then that Z-axis gyro might be way too small, and then you have a lot more of variations with process. So if you have a better process, you can definitely do that. So basically, once you find a way to implement Z-axis gyroscopes and X and Y gyros, and you can place them all together in combination with accelerometers, and we'll talk a little bit more about this in the next session, into monolithically integrated inertial measurement units. So this is an example developed by Georgia Tech, with the help of Qualtrics through project through DARPA, the micro-PNT teamwork project, and basically we can see here that you can just put absolutely every single device into the same die and get response for all your sensors. So far we have discussed how ideal gyroscopes operate, but obviously in reality there are many sources of error that are going to cause our lives to be a little bit more complicated, and we have to either learn how to live with these errors or learn how to compensate and calibrate them out. So if we take a look back at our dual gyroscope, as we've been saying, we have our drive second order system or sense second order system, and ideally they should be only coupled through the Coriolis effect. So in an ideal gyro, particularly for an active symmetric type of structure, the resonance frequency of the mode 1 and mode 2 is defined by the effective stiffness and the effective mass of each mode. And if you have a perfectly symmetric structure, then there's no reason why these two frequencies shouldn't be equal. Now, in reality, fabrication and material imperfections are going to cause to either that stiffness or that mass to be different from each other. So in the case where you have different stiffnesses, we usually refer to that as an isoelasticity error. If your masses are different, you define it as an inertial error. And then, yes?
How do you find it? And the other that a section of the mass is
the effective mass. So basically, is when you have bulk-acoustic modes, there's only a certain portion of your regular mass, so the mass defined by the volume of the device times the density. There's only a certain part of that that really contributes to the mode shape. So that effective mass is actually calculated from the equations that you use to calculate the resonance modes of the structure. Because not every single node in your device contributes equally to that mode shape in particular. If it was, for example, a translational mode, then obviously all of the mass contributes to the motion, so your effective mass is basically the volume times the density, but in resonant type of structures, that's not the case. But anyway, you can basically calculate that by using vibration analysis. As I was saying, any differences between the effective mass of your drive and the effective mass or stiffness of your sense are going to cause a frequency split. And obviously, in mode-matched gyroscopes, this is very detrimental for our performance. So there are ways in which we can compensate to some extent for this type of imperfections. So a typical way to do this is by the use of electrostatic spring softening, and I'll be discussing a little bit more about this in the accelerometer section. But in general terms, what you do is basically you apply a voltage in one of the electrodes aligned with one of the modes. So what that creates is an effective change in stiffness. So now the frequency of the mode that is aligned with that electrode is no longer just your K mechanical over your effective mass, but you have this additional component of that is a K electrical, and then that is a function of the polarization voltage of the disk minus the voltage applied to the electrode. So if you change the value of this potential, the mode that is aligned with that electrode is going to have a much larger changing frequency because you're changing K electrical as compared to the mode whose node is aligned with that. So basically, you can find a particular voltage in which these two frequencies are equal, and you can correct for that error and bring your part back to a mode match condition. Now, another source of error is what I define here as mode-to-mode coupling errors. So going back to our ideal gyroscope, we have our drive mode, in which when we apply a force, vibration, the acceleration, and then our sense mode, which only through the effect of Coriolis coupled to this original vibration. So if there's no other source of imperfection, there is no reason why you should get a wide displacement other than if there's a rotation rate. But in reality, imperfections in the disk create this additional terms in the expression that are termed as either stiffness coupling or damping coupling. And an easy way to express this is by basically modeling it as a component that is that contributes to both modes. So you can see it in a very simplified way that if you apply a force to your x in your x direction, you get this x displacement, but then this spring is going to cause that displacement to couple to your y mode, and then you're going to get a signal that on your sense mode that is not due to your Coriolis. Yep.
What's lambda?
Yeah, so lambda is what is known as the angular gain, and we will talk about that when we cover the whole angle mode gyros. So it's basically a factor that accounts for some effects that we will be discussing. It's just an additional constant that actually degrades the amount of energy that couples from one mode to the other, and we'll see why in just a few minutes. So going back to the damping and stiffness coupling, so stiffness coupling is basically when you have a force in your drive mode, you generate your drive displacement, and this K12 factor generates a force that excites your sense mode, even in the absence of rotation rate. And if you look at the condition where your gyro is almost close to a mode match condition, what you see is that the phase of that error signal that you're getting on your sense mode with respect to the phase of your drive displacement is actually 90 degrees off. And this is what is usually known as quadrature, because that's the output signal is in quadrature with your drive. So there are also ways to correct for this type of errors. So very similar to what you do to mode match your parts. If we see, for example, an imperfect part that has stiffness mode coupling, and here you see this here, where we have this red response for your drive mode, and you still see some excitation of the sense when there shouldn't be one. You can correct for this by applying a voltage that is now not aligned with your modes of interest, but is somewhere in between. So in an ideal case, if you apply this voltage and try to change the stiffness somewhere in between the two modes, if the part is perfect, then the two frequencies should move together. There's no reason why the effect on one mode should be different from the other. But if you have an imperfection, then the effect on one of the modes is going to be higher than in the other. And then what you basically end up doing is you can visualize this as trying to align the modes back to their original position. So this can be viewed as some sort of misalignment in the part itself. And by applying that electrostatic voltage, then you can bring back your part to an aligned mode. And then you can use, as we showed before, a voltage in an electrode aligned with your modes to bring this back to delta F of 0, or frequency split of 0. Damping coupling is an effect that is a little bit harder to understand, but in general terms is a signal that it's proportional to the velocity of one mode acting on the other. And the reason this type of imperfection is so critical is because in reality it doesn't really cause the modes to split, so it doesn't really create a delta F, if assuming that your Qs are high. But if we take a look at a device that we have already been able to mode match by compensating for stiffness imperfections, what we see is that the ratio of the error signal that you get due to damping coupling with respect to your drive signal is actually 0 degrees off. And if we compare this with what you would get from a rate signal, we see that the two of them have the exact same phase. So that means that it's impossible to distinguish an error signal coming from damping coupling from a signal coming from an input rotation. What makes it even more complicated is that since you can't distinguish it one from the other, it's very difficult to implement electronic techniques to compensate for it. There are methods to do it. There's more reversal type of applications in which you can make this signal look like a common mode to respect to the rate. But probably the best way to get rid of this problem is by doing it in the sensor and trying to design a gyro with low damping coupling. So since Q plays such an important role in mode match gyroscopes, it's always important to understand where the sources of loss in a resonating structure come from. So as we know, the overall Q of a structure is a combination of different loss mechanisms. So this first term, this QSFD, is mostly squeeze film damping. So it's basically the energy loss due to the interaction of the resonating device with the molecules in between the resonator and a capacitive gap. One important thing about this type of losses is that they're frequency dependent. So basically, as you go to higher frequencies, these molecules have an inertia and they can't really respond as fast as your resonator. So your Q actually is higher for devices that operate at higher frequencies. This second term, QTD, is thermoelastic damping. So it's related to thermal losses due to localized thermal gradients that appear due to either compressive or extensive stresses in the device. And the way you can optimize for this is by selecting a material that has low coefficient of thermal expansion, or by trying to decouple the mechanical modes from the thermal modes of the device. So you can actually try to make them in frequency as far as possible so that you don't get a lot of energy transfer in between the mechanical and the thermal domain. The third thing here is anchor loss. So that's related to the amount of energy that you're losing from the resonator into your substrate. And that is related to the strain energy density at the location of your anchor. So obviously, if you want to design for high Q, you need to find the right location where this anchor should go, and it's basically where your strain energy density is the lowest. The remaining two terms are the Q surface and Q intrinsic or Q material. And there's really not much you can do about these terms in terms of design. These are mostly related to fabrication and material properties. So if you have reached that fundamental limit, perhaps what you should do is change the material of your structure if you still need to get higher Q, or optimize your process to get rid of this surface imperfections. So now let's move from rotation rate gyroscopes into whole angle mode operation gyros, and probably it's good to start by defining why whole angle mode gyros are attractive. And if we take, for example, an application like an inertial navigation system, obviously to keep track of the motion of an object, what you really want, the information that you really want from your sensor is the displacement and the angle of rotation. So if you're utilizing the system a rate gyro, what you need to do is you need to take the rate signal and then integrate it over time to get your angle of rotation. And obviously, this process has a lot of errors associated with it, because any noise from the interface circuit or any drift from the rotation rate itself is going to get accumulated over time as you do this integration process. So in the case of whole angle mode structures, your output is already the angle, which is what you want for this navigation application. So you don't have to worry about integrating any signals, and you can actually get lower drift, assuming that the main source might be from that interface. So the way whole angle mode gyros operate is very similar to what we saw for the Foucault pendulum. So if we have, for example, a shell-type structure that is resonating in its first elliptical mode or its n=2 mode, and we rotate this structure by 90 degrees. So if we see here this reference point, which is the frame in which this structure is inside, and we rotate it 90 degrees, what we see is that the pattern of vibration doesn't rotate by the same amount as the input angle. And this effect is what actually allows us to use these devices to measure rotation rate. But now, what's really interesting here is trying to understand why is it that this happens. And something I forgot to mention is that the ratio of the input angle to the angle of change in the vibrating device is what is known as the angular gain, which is what you were asking me for, and it's basically a very stable parameter because it doesn't really depend on any physical property, so it doesn't have any temperature dependencies, or it's mostly defined by the mode shape or the vibration pattern of your structure. So that's a very good thing when you're utilizing whole angle mode gyros, that most of the gain is just determined by this angular gain factor. So something very interesting is trying to understand why is it that this vibration pattern doesn't really rotate at the same rate as your input rotation. And the first person to really understand what was going on was Brian, and he did this back in 1890, and he ran this very interesting experiment in which he first took a vibrating wire. So he basically just took a simple rod, and he excited this into vibration, and obviously this has a resonance frequency in the audioble range. And what he noticed is that as you rotate this stage, all you hear is a continuous vibration. So this is very similar to what we saw for the Foucault pendulum. This outside observer in outer space, he only saw the pendulum moving back and forth about the x-axis, no matter if the Earth was rotating. Well, in this particular case, this is an outside listener, so there's no reason why he would hear something any different than the vibration of that wire. Now, after that, he took a tuning fork type of structure, and he excited the tines of the fork into vibration. And obviously, since the axis of symmetry of the two tines are no longer right at the center of the rotating stage, then what he heard was this intermittent sound. So every time the vibration axis of the tines aligned with the ear, then you will see you will hear the vibration, and when they're exactly orthogonal, then you won't hear absolutely anything. And then after that, he took a wine glass. For this example, is a model that's because it's very difficult to show wine glasses in PowerPoint, but the effect of it is exactly the same. And he excited that wine glass into this n=2 mode, or this elliptical mode. And as he rotated the structure, what he heard was that there were only 2.4 beats per revolution, instead of this continuous sound or this intermittent sound that went along with the rotation. And what he realized that's happening is that if we, for example, take the antinodes of vibration, which have the maximum rate of displacement. Well, those particular points, they behave exactly as the wire. They want to stay fixed in space because they have a lot of energy of oscillation around that particular axis. But now if we take the the nodes, which is where you have zero radial deformation, well, they really don't know what's going on because they're not moving, so they obviously want to just rotate with the stage. And then all the other points in between that antinode and that node are somewhere in between. They're not sure they want to move along or stay. So in average, the vibration pattern can't really rotate at the same rate as the stage. And that's what really makes this shell type of gyroscopes useful to measure full angle mode rotation. And another way in which you can describe this is that basically not every point in the structure perceives the same Coriolis acceleration. The points with higher velocity are going to experience higher Coriolis acceleration. The points with lower displacement or velocity are going to experience much less. So in average, you don't get the same amount of rotation. So now the question is, now that we know that this resonating structure is going to lag with respect to the rotation that you apply, well, how can you measure the angle of that vibrating device? And we can easily do this in a very similar way to what we described for the Foucault pendulum. We can decompose the motion of vibration into two orthogonal modes. So if Q2 is the amplitude of the mode aligned to the 45-degree line, and Q1 is the amplitude of a mode aligned with the X and Y directions, then by measuring those two amplitudes, the ratio of those two amplitudes, we can always calculate the angle. So, for example, in this particular picture, what we see is that we have Q1 to be a particular value, right? This is vibrating about the orientation of our mode 1. And then Q2 is 0 because we don't have any vibration along that axis of interest. So if we take the arc tangent of 0, we get 0. So there's basically an angle of 0 rotation. Now, if we apply a rotation in such a way that these modes are now aligned with the 45-degree line, well, now this Q2 is maximum, but Q1 is 0. So if we take the arc tangent of 1 over 0, or a number over 0, we're going to get 90. And then divided by these two is 45. So now we know that our pattern angle has rotated by 45 degrees. And by taking this angular gain factor, then we can back calculate by how much we have actually rotated the whole stage. Then we can use this capacitive electrodes and name them the cosine and sine electrodes and monitor them continuously. And taking the ratio of their amplitudes, we can calculate the angle for any particular rotation of light. So as far as I know, there are no commercial whole angle mode gyros implemented with MEMS structures, but there are some research groups in universities that have achieved this type of operations. And here's an example from University of Michigan where they implemented this whole angle mode gyro that can actually operate both in rate mode and rate integrated mode, which is the same as whole angle mode. Here's another example from UC Irvine in which, unlike what I have been describing, they utilize a tuning fork type of structure to operate it in a whole angle mode. So, as I said, axis symmetric devices like rings and shells are beneficial because your modes are already inherently mode matched. But that doesn't mean that you can't use this type of devices and design your springs to be identical and also be able to operate this in a whole angle mode operation. Here we can see the response of that device to a particular rotation. So one of the complications of whole angle mode gyroscopes implementing using MEMS devices is that as we know, we need to excite this structures into vibration and let them vibrate freely without corrupting their mode shape, because basically that vibration needs to move around as you rotate the device. Now, the problem is that MEMS devices have limited Q. So obviously, if you excite that into oscillation 1, as time progresses, you're going to have a decay time. And then at some point, you're going to have to go back and replenish that energy so that you can take your measurement once again. The problem with that is that if you try to replenish the energy by using an electrostatic voltage aligned with the electrodes, then what's going to happen is that you're going to break the pattern of rotation. So basically your measurement gets completely corrupted. So you need to take these intervals of time in order to re-excite the structure. And if you have a very limited Q, then the time you need to replenish this is going to be smaller and smaller, and then the part becomes fairly unusable. That's why there are these new programs sponsored by DARPA, in which what they're trying to achieve is to implement this hemispherical type of micro gyroscopes, in which not only you can get very high Q from your micromachining process, but also since they're very flexible and they have very low frequency, so then your decay time is much lower. So this is still a work in progress, and hopefully in the future we will see more of these devices in commercial applications. So here's a brief summary of what we discussed today, and that's pretty much it. So I'll be happy to take any questions.
So starting from the last one, with Gyros, in principle, the device is higher kind of non-linear because it retains in to what extent is this the angle is so small that there's the linear?
Yeah, so that then just goes back to the electronics, right? How accurate of a 10 function or R10 function we can actually generate to extract that small number. Yeah, that is true.
You discussed the effect of imperfections in the sequence, and the protective terms in the sequence, and position for movement. Is the effect similar in mostly?
Yes, it's basically the same. Yeah, you have the exact same complications. So
and also the phase shift affects the output is the same.
well, since you're measuring angle, things are slightly different, but what you're gonna get is a distorted vibration pattern. So if you have a frequency split, for the case of whole angle modes, what you want is a pattern of vibration to be able to move freely around your structure, right? Now, obviously, you can decompose that into two orthogonal modes, but if the resonance frequencies of the two of them are different, then obviously there's going to be a distorted type of vibration happening, because you don't get the same amount of energy for the two modes. But the sources of imperfections are the same.
You were talking about the various noise sources. You have this tremendous mix of dependence on Q and F naught.
Different.
After that slide.
This one? Yep.
It seems to me that I could somehow solve those four equations simultaneously and tell you exactly what the right answer for F2 are for the perfect gyro.
Well, these are some of the most important metrics, but not all of them. For example, here you don't have non-linearity, right? So then you also have to worry about what else? I'm sure that, yeah, you can come up with a solution that will give you a very good gyro, but there might be things that you still need to look after.
Here's something a little bit more about the effects of death on manual gyros. If you go like this one and next one,
Well, that is related to that damping coupling. So basically, having a different Q in mode 1 and mode 2. Let me see if I can find that. Having differences between mode 1 and the Q of mode 1 and mode 2, you can see that in a way as part of the energy in one mode being dissipated faster than the energy in the second mode. So effectively, you could say that some of the energy of the mode with higher Q is actually being leaked into your second mode. And that leads to this damping coupling, that D1-2 term, which is basically due to these differences in the quality factor, and then the effects that I described are related to having a signal that comes exactly at the same phase as the array, so you can't really distinguish one from the other. So that's why it's critical to have equal Qs. Now, this is more important in whole angle mode gyros, where you have this continuous energy transfer between the two modes. In rotation rate gyroscopes, since you're always replenishing the energy loss for the drive mode, the effects of Q differences might not be as critical. Yep.
You mentioned about the shock and vibration test. I presume these tests were done at room temperature?
Yeah, everything was done at room temperature.
How many, any trends that you observed about the operating temperature of the component?
Well, we have data on the offset across temperature, and obviously what these experiments show is the change in offset due to this vibration or shock inputs. So if you basically have a stable gyro that performs well across temperature, then I don't see any reason why these numbers might change. But let's see. Yeah, since the loss mechanisms or the sources of imperfection of vibration and shock are mostly related to your anchor point, yeah, I think actually there might be changes with temperature. I don't think they might be dramatic. If your offset is well behaved across temperature, I don't see a reason why you might see something going way off from what you measure at room temperature, but yeah, there might be that dependency. Yep.
What is scale factor?
Scale factor? Scale factor is your sensitivity, so it's basically the amount of output per unit of input or rotation rate or angular rotation. So if you have a gyroscope that uses, for example, capacitive sensing, and you're trying to measure an output current, then your scale factor is going to be that output current divided by omega, which is your input rotation rate.
Like goes back to question. We use rate gyroscopes, and if you use rate gyroscopes, you use grain integration to the information. We have a lot of problems
Yeah.
Why this problem are smaller? Do they need inertial forces a lot?
Yeah, so you probably can get better resolution on a accelerometer, but I don't think the problems are too smaller. I think that for MEMS accelerometers, you end up having the same type of complication. But if you can come up with an integrated velocity sensor, then you get rid of one of those integration processes. But now the question is, how do you design a velocity sensor? Doppler effect, perhaps. All right. Okay, so if there are no more questions, thank you everyone for being here, and I'll see you probably in the next session. Which slides? Go up. Up. ¿Cuál es?
Tienes el driving, y luego tienes que ir un poquito en el sense mode.
Ok.
Se incrementa. No sé si es la pregunta conceptual es, dependiendo de hacia este movimiento, ¿tienes más cercanía? ¿Tienes que central?
Sí, error en la pero sí, debe estar centrada.
Se supone que la amplitud es la misma.
Sí, la amplitud es la misma. No, sí, ese es el problema en la diapositiva. Yo voy a arreglarla, pero si la encuentro. La arreglo cuando la encuentro.
Yeah. So it means the scale factor defines the conductivity. Or we can say it's the resolution.
Resolution is defined by the noise.
Right?
Yes, the mechanical
That's the
noise.
difference.
Yeah, and then there's another term called dynamic range, which is basically the ratio of your maximum detectable signal over your minimum detectable signal.
Yeah. It's
so
the resolution.
Well, yeah, it's a function of the resolution as well. That's correct.
Oh.
What time is it? Huh? 12:20. Oh, so that was okay.
Yeah, we're
Okay.
Oh, by the way, what's the meaning of this Y and X?
So X is the drive displacement. So the displacement of that oscillation that you first established. And then the Y is the sense mode displacement. So it's a ratio of those two values. It's a good metric to know if you have a Joule jar or not. You can, I'm going to be covering the next session, and the presentation is already there. I put these over here. So, all right.